Hello student, I am Nirmala Morade from Department of Mathematics, S.V.K.T. College Devali Camp, Nasik. In last lecture, we studied examples using rank nullity theorem. The rank nullity theorem for matrix is rank of matrix A plus nullity of the matrix A is equals to the number of columns of a matrix A. So in last lecture, we are going to study linear transformation. What is meant by linear transformation? Its a definition, some examples of linear transformation. So linear transformation is a mapping with some properties. So for that, let us consider the definition first. So first consider the two vector spaces. So suppose first vector space is V, second vector space is W over some field. Define a mapping say T from V to W. This mapping, this is called a linear transformation. This mapping is called linear transformation if it satisfies the following two properties. So first property is T of u bar plus v bar is equals to T of u bar plus T of v bar for all u bar v bar belongs to V. And now the second property is T of ku is equals to k times Tu, where k is a scalar and u is a vector in V. So this is our second property. So any mapping T from V to W satisfies these two property, it is called as a linear transformation. Again see what is the definition. T is a mapping from vector space V to vector space W over the field say F. So this mapping is called the linear transformation if it satisfies these two property. First property is T of u plus V is same as T of u plus T of V for all u V belongs to V. Second property is T of ku is equals to k times Tu, where k is a scalar and u is a vector in V. So any linear transformation, any mapping with these two properties is said to be a linear transformation. So now in this case, if V is equals to W, then T is called the linear operator. T is called the linear operator. Now let us consider some standard example of linear transformation. Now our first example is so now we consider a linear we consider a mapping T from V to W defined as Tu is equals to 0 bar for all u bar belongs to V. Now remember this 0 bar is a 0 of the vector space W. We can easily show that it is a linear transformation. Now let us see how to show that it is a linear transformation. It is a linear transformation means it satisfies both the properties, first as well as the second property. Okay, now so for that we consider two vectors. We consider u and v are the two vectors from V and consider one scalar. So suppose k is a scalar here. Okay. So now calculate T of u bar. By definition of T, every element of V maps to 0 under this linear transformation. So T of U bar is 0 bar, as well as T of V bar is also equals to 0 bar. Then calculate T of U bar plus V bar. So as we know that V is a linear transformation, and according to the definition, V is a vector space, and according to the definition of vector space, if U bar and V bar are the two elements from V, their addition is again in V, and since this is the element in V, so under this mapping T, it maps to 0 bar, so its value is also equals to 0 bar. So from these two statements, we can say that this is same as T of U bar plus T of V bar. Thus here first property is fulfilled. Now try for the second property. So for that calculate T of Ku. Again here K is a scalar, U bar is a vector in V, and since V is a vector space, capital V is a vector space, so it is closed for scalar multiplication. So any scalar and a vector from V, is their multiplication is again in V, and so by definition of this transformation, or by definition of T of U is equals to 0 for all U belongs to V, and so T of Ku is equals to here 0 bar. T of Ku is equals to 0 bar. Now we calculate this one, T times Ku bar, this is equals to K is as it is, and T of U bar is equals to 0 bar. K into 0 bar is again a 0 vector. So from this we can say that T of Ku bar is same as K times Tu bar. So the second property is also fulfilled. So this mapping satisfies both the properties. T of U plus V is same as T of U plus T of V, and T of Ku bar equals to K times T of U bar. So it is a linear transformation. This is a special type of linear transformation, and this is called the zero transformation. Remember, T is a mapping from V to W defined as T of U bar equals to 0 bar. This mapping is a linear transformation and it is called the zero transformation. Now next we consider the another example. So in second example, let T is a mapping from V to V defined as Tu equals to U bar. T of U bar equals to U bar for all U bar belongs to V. This is a linear operator, because here V and both V and if V is equals to W, then T is called the linear operator. So now show that it is a linear transformation. So it satisfies both the property first as well as the second. So for that, first we consider U bar and V bar are the vectors from V. These are the elements from V. Then calculate T of U bar. According to this definition, U maps to itself. So Tu equals to U bar. T of V bar is also equals to V bar. Second, calculate T of U bar plus V bar. Since U and V both are the elements from V, so there again addition is again in V, because V is a vector space. Okay. So T of U plus V bar is again equals to U plus V bar. This is same as U bar equals to T U bar, and V bar is same as T of V bar. So here the first property is fulfilled. T of U bar plus V bar is same as T of U bar plus T of V bar. Now consider the second property. Start with T of Ku bar is equals to K is scalar, U bar is the vector in V. V is a vector space, so it is closed for scalar multiplication. That's why this vector belongs to V. This is a vector in V. This is a vector in V. And according to the definition of T, T of U bar equals to itself. So this is equals to K times U bar. So it is same as K times U bar. Replace U bar is equals to T of U bar. So here T of K times U bar is same as K times G U bar. So both the properties are fulfilled here, the first as well as the second property. So this is a linear transformation, and since it is from V to V, from same vector space to itself, so it is called the linear operator, and this linear operator is called the identity operator or identity transformation. It is called the identity transformation. So now next consider the another example. So for example third, we consider a mapping T from V to W. Okay, we consider a mapping from V to V itself, defined as T of U bar equals to K times U bar for all U belongs to V, and second, K is a scalar here. So now we want to show here it is a linear transformation. It is a linear transformation. So now for that, starting with, take two elements from V. So let U bar and V bar are the two vectors or the elements from V. We consider the another scalar. So we consider scalar instead of K, we consider say L is the scalar. So okay, we want to prove that it is a linear transformation. So starting with the first property. So according to the definition of T, T of U bar is equals to K times U bar, and T of V bar is equals to K times V bar. So see this definition carefully. Here input is U bar, the output is K times U bar after operating T on it. So K times U bar. So here T V bar is equals to K times V bar. Then calculate T of U bar plus V bar, which is same as, again use the definition of T. So here T of U plus V bar equals to K times U bar plus V bar. U bar plus V bar. Now this is a scalar. These are the two vectors and V is a vector space. So this can be written as K times U bar plus K times V bar, which is same as K times U bar is T U bar and K times V bar is same as T of V bar. So here the first property is satisfied. T of U plus V is equals to TU plus TV. Okay, so go for the second property. So for that calculate K time T of KU, that is we consider some scalar and a vector. So here we consider T times, instead of K we use another scalar, K times L times U is equals to, and our aim is to show that it is same as L times TU bar. Okay, so T times LU, this is one vector, this is one vector. Now apply this definition. According to this definition, this is equals to K times LU bar. This is equals to K times LU bar, and this is equals to, these are the two scalars, this is one vector. Without loss of generality or the one property of vector space, it can be written as KL times U bar. KL times U bar. These are the two scalars and they are commutative. So this can be written as L times K U bar, and again this can be written as L times K U bar. Okay, and this is same as, this keep L as it is, and KU bar is nothing but T of U bar. So thus here T of K L times U bar is same as L times T U bar. So second property is also fulfilled. So this is a linear transformation. This is a linear transformation from V to V. So it is a linear operator. It is a linear operator. Now remember this linear operator, which is defined as T of U bar equals to K times U bar. If we take K is greater than 1, it is called the dilation. If we take for this linear operator, K is greater than 1, then T is called as the dilation. And if k lies between 0 and 1. If k lies between 0 and 1, then this T is called as the contraction. T is called as the contraction. Now, if you remember, suppose I multiply a vector by a scalar which is greater than 1, definitely it is a stretches. It is a stretches. And if we multiply a vector by a scalar which is lies between 0 and 1, then that vector is compresses. For example, in case of dilation, suppose these are our vectors. This is our first vector, say v1 bar, and if you consider k times v1 bar, is definitely its length is larger than the first one. That is v1 is stretches in, that is in dilation the vectors are stretches, and in contraction vectors are compresses. So suppose this is v bar, this is k times v bar where k is greater than 1. Same for if I consider the another vector, say v2 bar, then definitely k v2 bar, its length is greater than v2 bar. So this is a dilation in which the vectors are stretches. Vectors are stretches. In contraction, suppose we multiply a vector by a number which is lies between 0 and 1, it compresses. Okay. So suppose I consider this is our vector v1 bar, and now we have to calculate k times v1 bar where this k is lies between 0 and 1. K lies between 0 and 1. So in this case it compresses. So this is the vector kv1. We can take one simplest example of R2 also. Suppose I consider v is equals to R2. Take k which is greater than 1. So suppose I consider k is equals to 2. So take a vector v bar is equals to say 2 1, a simplest vector 2 1, and now calculate k v bar which is equals to 2 times 2 1. So use the scalar multiplication, component wise scalar multiplication and component wise addition. So this is equals to 4 1. So if you see in the diagram, so our first vector is 2 1. So this is our first vector 2 1, and next vector is 4 1. So this is our next vector is 4 and 1. Okay, if you draw the diagram by using the graph, you can observe that this is the relation between these two. This is first vector and this is the second. Just compare its length. The length of first vector is smaller than the length of second vector. Okay, similarly, if I take k lies between 0 to 1, say suppose I take k equals to 0.1. So in this case, our k times v bar becomes 0.1, multiply the vector to 1, so it becomes 0.2, and here is 0.1. So here vector is compresses and here vector is enlarged. Okay. So this is another example of the linear transformation. Now there is one result related to linear transformation. That result says that So this is one result. If T is a linear transformation from V to W, or T is linear transformation if and only if T of alpha u plus beta v is equals to alpha times Tu plus beta times Tv, where alpha and beta are the scalars and u and v are the vectors here from capital V. Now let us prove this result. So this is a two-way result if and only if. So now let us consider the first part. Suppose T is a linear transformation. In first part, the given thing is T is a linear transformation and we want to prove this one. So since T is a linear transformation, there are two properties of linear transformation. First, it preserves the addition and it preserves the scalar multiplication. That is, T of u plus v bar can be written as T of u bar plus T of v bar, where u and v are the vectors in capital V. And second property, T of k times u bar is can be written as T of k times Tu bar. These are the two properties of linear transformation. So since T is a linear transformation, these two properties are satisfied. Now we want to prove this one. So now starting with this T of alpha u bar plus beta times v bar, this can be written as, remember these two vectors are u bar and v bar are from capital V and alpha and beta are the two scalars. So here alpha u bar as well as beta v bar and the alpha u bar plus beta v bar are the elements of vector space V. So now first of all we treat this as a, so these are the two vectors alpha u bar plus beta v bar, and so because of first property this can be written as T times T of alpha u bar plus T of beta v bar. So we use here the first property. Now then use the second property, T of Ku equals to K times Tu. So it is equals to alpha times T of u bar plus beta times T of v bar. Okay. So thus here if T is a linear transformation, then this properties hold. Now conversely, suppose this property is true, now we want to prove that T is a linear transformation. So let us prove the converse part. So conversely, suppose T of alpha u bar plus beta v bar is same as then prove that T is a linear transformation. Now here we put alpha and beta both are equals to 1. So this equation becomes T of u bar plus v bar is equals to T of u bar plus T of v bar. Again in the same equation we put here beta equals to 0. So if you put beta equals to 0, then the equation becomes T of alpha u, this term becomes 0 bar. So this is same as alpha u bar is same as alpha times T of u bar. Since beta is 0 into some vector is again a 0 vector. So this becomes T of alpha u bar equals to alpha times T u bar. So T is a linear transformation here. T is a linear transformation. So for any linear transformation this equation is true and conversely also. So suppose I want to prove that, we want to prove that a given mapping is a linear transformation, either you can use the result, this result, that is only prove the single property, single equation T of alpha u bar plus beta v bar equals to alpha times Tu r plus beta times Tv bar, where alpha and beta are the scalars and uv are the vectors instead of the definition. So in today's lecture we have studied definition of linear transformation and some examples. So if T is a linear if T is a mapping from V to W for a vector space V to vector space W, It is called the linear transformation if two properties are satisfied. First property is T of u plus v is equals to Tu plus Tv for all u bar and v bar belongs to capital V. And second property, T of alpha times u bar equals to alpha times T of u bar, where u bar is a vector in V and alpha is any scalar. So instead of these two property can be combined as a single property, and which is same as T of alpha u bar plus beta v bar equals to alpha T u bar plus beta T v bar, T of v bar. So to prove that given mapping is a linear transformation, either prove the two properties or the single property, that is this one. Also we have to study some examples of standard linear transformation like identity transformation and the second identity operator and the zero transformation, as well as the problem dilation transformation and contraction transformation also. So in next lecture we will study more examples, that is the matrix transformation, transformations from R raised to n to R raised to m. So today we stop here. Thank you.